All right, yo, I'm gonna check one more time. You can hear me? All
Yeah.
right, perfect. All right, so good morning, everyone. We're going to continue our discussion about the use of crystal field theory to help us to appreciate different properties, in this case, spectroscopic properties of metal complexes. So we were touching upon this at the end of our last lecture, where we were focusing on the electronic absorption spectroscopy of coordination compounds. So I'm going to just mention that the two that we're really going to highlight are the metal d orbital electronic transitions and also the charge transfers between metals and ligands, right? So that's where we were at the end of our lecture. And so here we were focusing on an example where we're looking at a system that contains a metal, in this case, the titanium-3, surrounded by 6 aqua ligands, all right? So we have this system right here. And then we identify what is the electron configuration. So that has 1 d electron. We're putting this into an octahedral field. So according to this particular theory, we have this separation of energy of the d orbitals, right? So we have 3 of these d orbitals that are the T2G, that's how we label them, and 2 of them that are EG. All right, so we discussed this in the last lecture, where there is a loss of degeneracy because of the points of contact between the negative point charges with the metal d orbitals, resulting in some being destabilized because of the direct contact, and 3 being stabilized because there's not a direct contact. All right, so now we have the separation. And so, according to Aufbaum's principle, we're going to put that single electron in the lowest energy orbitals, which would be right here. So if we're going to track a transition, we're looking at a transition from the lower energy T2G to the high energy EG. And that's a very simple transition. So we would expect to see something simple like this, where we have an absorbance that corresponds to that one single electron. And I had already mentioned to you that the reality is that that's actually not as simple as it appears. It is really a combination of a few different electronic transitions. And that's something that is a little bit beyond the scope of what I'm going to focus on right now. So just imagine that we're overall looking at that single electron being moved into higher energy orbits. All right, so let's focus on where the apex of that particular absorbance is. And so that will mark the energy that in theory corresponds to the delta octahedral, and that is the separation between T2G and EG. So that gives us the energy that corresponds to that transition, but something else that we are going to focus on is the intensity. So that absorbance that we're registering, because that intensity is going to give us an indicator of how allowed a particular transition is. All right, so we discussed this use of the color wheel as it gives us information as far as the complementary nature of these absorbances that we typically see for DD transitions, which occur in the visible range. So I mentioned this. I also discussed this in the context of the spectrochemical series, how in going from left to right, we're looking at an increase in the magnitude of your delta octahedral. And because of that, we see a difference in the coloration of the compounds based on their ability to really affect the magnitude of delta. And so that's why we have these representations that are a little bit exaggerated of what happens if you change the ligation, right? So you have cyano ligand, the amine ligand, and the aqua ligand, and how that's going to affect the absorbance of a metal compound, in this case, cobalt 3+, as it is surrounded by those particular ligands. All right. So let's go into where we were at the very end of our lecture. And we were discussing these rules that are the electronic transition selection rules. And so the reality is that most electronic transitions that we observe actually violate these rules. But the way that we can get a sense of what type of transition is occurring and whether or not it's following these rules is based on the intensity of your absorbances. All right, so let's review what these rules are. One of the rules is the spin rule, and that is that transitions must not involve a change of spin. All right, so we should see a delta S of 0, and we'll look at that in a moment. What does that really mean? All right, the other one is the Laporte rule. And so we had already mentioned this last time, where this has to do with transitions requiring a change of orbital type. And so in terms of technicality, this is actually having to do with a change in the symmetry parity of the actual orbitals. But for the purpose of this course, let's refer to this as a change of orbital type. And I'm emphasizing that because when we're looking at d orbital transitions, we're looking at something that in its nature is already violating the Laporte rule. So this is going to be something that is Laporte forbidden because they're going from d orbitals to d orbitals. There is no change in orbitals here. All right, so we're going to look at a few case examples of things that violate, I'm focusing on d orbital transitions, things that violate the spin rule and things that don't, and how we can gauge what we're actually observing. All right, so we're simply relying on that very simple relationship that you learned a long time ago, which is called Beer's law. That relationship between absorbance and then the concentration of a given species, with this particular number here, or this particular constant, which is the extinction coefficient, or is also referred to as the molar exertivity. So this is a solvent-dependent constant, okay? And it can also actually be pH-dependent, but let's focus on solvent. So anytime you dissolve a compound in a solvent, you should get this number consistently because that is characteristic of that particular species. If you see something that is not that the number that has been measured, that means that something is different in solution. Okay, so that constant is something that you have to actually abide by. And so the value or the magnitude of this particular constant will allow us to understand if a transition is following these rules. So it basically serves in very simple terms how allowed a particular transition is. So this non-word allowedness, and I'm just using it for the purposes of clarity, of whether or not you're following these particular rules. All right, so let's look at one example. And so here we're looking at the example of manganese. Okay, so you look at your periodic table, you find where it is, and we're focusing on manganese 2+. So we would have to figure out the electronic configuration for that particular metal ion. It turns out that it is D5. Okay, now experimentally, we would have to determine whether that's going to be low spin or high spin. The example that I'm showing you here is manganese in a coordination environment with 6 aqua ligands. That particular compound is high spin, okay? And again, that's something you have to know or observe experimentally. All right, so focusing on a high spin D5. All right, so we have our corresponding splitting into d orbitals because we're in an octahedral field. And so high spin means that we prefer to have the electrons fill in all the orbitals before they start pairing up. So in this particular case, we have all of the electrons completely unpaired, right? And so we were to calculate how many unpaired electrons, well, we have a total of 5, right? So each electron has an m sub s of 1/2, and s, if we remind ourselves, is a summation of m sub s. So our total value of s would be 2.5. Okay, so then let's imagine the transition of one of those electrons from T to G, right, into EG. So what's going to happen? Well, what we're going to see is that one of those electrons that's going to go into these orbitals up here, well, there's going to have a sharing of an orbital, but very importantly, you're going to have a flip of the spin, right? Because you cannot have 2 electrons in the same orbital with the same spin, right? That would violate what we know as far as the quantum rules. And so here then, we have a pair of electrons, right? And what happens? Net effect. The net effect, Javier, how many unpaired electrons do we have now?
Now have 3.
All right, so we have 3 unpaired electrons. As a consequence of that, our spin now is 1.5. So if we were to calculate delta S, we would go 2.5 minus 1.5, and we have a number that's 1, right? And so that number clearly is not 0, right? And so we're violating the spin rule. So this particular transition violates 2 rules, the spin rule and the Laporte rule. So as a consequence of that, what do we see? Well, we see that the typical extinction coefficient for systems that violate both are going to be super low. So you're going to have an extinction coefficient of 1 or less than 1 per molar per centimeter. Okay, so if we're relating, and we're going back to Beer's law, in order for us to see something of that extinction coefficient, what do we require? Well, in this equation, for us to be able to observe it, and we have to be familiar with the limitations of UV vis, that's the typical technique that we use. We need to then adjust the concentration at a really high level so that we will be able to see a transition of this nature, okay? All right, well, let's look at another system. And this is a system that we are not going to violate the spin rule, but we're still violating the Laporte rule. All right, so we're looking here at, we're switching the metal. We still have the same ligation system, 6 aqua ligands, and we have cobalt. This cobalt is cobalt 3. We look up the electron configuration, and that is a D6 electron configuration. Experimentally, we have to determine, what this is. It turns out that it's a high spin D6. All right, so we have this spin situation. We look at then the splitting of the electrons. Okay, so high spin, what do we end up with? Okay, Alex, how many unpaired electrons do we have here?
4.
Okay, we have 4 unpaired electrons. Okay, Jaylene, how many unpaired electrons after the transition over here? We have 4, okay? So then here, we have the same number of unpaired electrons. Here, our delta S is going to be 0. So we have not violated the spin rule. We're still violating the Laporte rule. So what is the net effect of this? The net effect of this is that your extinction coefficient is going to be higher than what we observe for the situation where we violate both spin and Laporte. All right, so now our values are typically going to be between 10 and 200 per molar per centimeter. Okay, you might find a few examples a little bit higher, but that's the general range in which we're going to see something that corresponds to these two. All right, let's look at another example of a D-D electron transition. And so here we're looking at a situation where now we're changing the geometry. So we have a ligation system where we're focusing on a metal. This metal is nickel 2+, and it's surrounded by 4 chloroligands. Okay, so we have a coordination number 4. All right, I'm going to go to Carmen. Coordination number 4. What type of geometries can we have? There are 2. Square planar or tetrahedral. Okay. All right. So in this particular case, this is a metal ion that has a D8 electron configuration. Okay. And so in this particular instance, then we're going to have something that is a little bit unusual for this system because it's actually going to be tetrahedral. Okay. That's what we're focusing on here. But the typical D8 system would be actually square planar. All right. So I'm focusing on this right now for a tetrahedral system because I want to show you something that's interesting when we compare it to the octahedral system. All right, so we have this splitting, and we talked about this previously, how the splitting for a tetrahedral field will be different than it is for the octahedral, where we have those 2 orbitals that we label E being lower in energy, and those 3 orbitals that are labeled T2 being higher in energy. So that's because in a tetrahedral field, we have a different orientation in terms of how the orbitals of the metal interact with the negative point charges. So in this case now, we're looking at those 2 orbitals. We basically flipped what we saw for the octahedral system. So we're looking at an electron, in this particular electron here, that's going from E into T2. And so we end up with this system over here. Okay, but when we look at the collective number of unpaired electrons, we've actually have the same number of unpaired electrons. So we have 2 unpaired electrons, we have an S value that's 1, so we still have a delta S that equals to 0. All right, but if you note the extinction coefficient, that extinction coefficient, it ranges from 100 to 1,000. Okay, so when we compare that to the octahedral example, where we are not violating spin rule, but we're still violating the Laporte rule, right? Both of them are the same situation, except the geometry, and we see that the range is actually bigger. All right, so why is that? Well, it turns out that for situations with a tetrahedral field, even though we're still D to D transition, so we haven't changed the orbital type, by changing the geometry, okay, now we have a system, and so here is a little bit of terminology that we're not too familiar with, which is non-centrosymmetric, okay? Because the tetrahedral geometry is non-centrosymmetric, it provides for a more allowed transition versus something that is ideally octahedral. This is a centrosymmetric system, and centrosymmetric systems will have this particular result, right? And so that lack of central symmetry is why you do have a higher magnitude for your extinction coefficient, even though comparing the tetrahedral with the octahedral, you'll still have something that is spin allowed. Okay, any questions? Go ahead.
When you mentioned that that is more allowed because it's central symmetric, what do you really mean? Because although.
Okay, so this goes into, so this might be a little confusing for you. This goes into things that you learned in inorganic chemistry in a traditional course. So we'll go back here, and there was a term that I used here, the parity, the symmetry parity. So you probably heard about things that are Gerade or unGerade, correct? And so you have some orbitals that are Gerade and some orbitals that are non-Gerade. You might hear about this soon in your course. All right. So when you have that type of situation, then you have to have a change of a system that is going to be Gerade to unGerade or unGerade to Gerade for it to be allowed. It can be Gerade to Gerade and it can be unGerade to Gerade. D orbitals are classically Gerade. So this is Gerade to Gerade, right? Right. So look at this here. I didn't highlight it too much because this is from the octahedral system. Ideal, those orbitals are EG T2G. Okay, so you have the Gerade label. So you're going Gerade to Gerade, which is not allowed. But if you focus on tetrahedral, that is not the actual symmetry of those particular orbitals. Gerade and unGerade do not apply because they are non-centric symmetric. So the fact that we've lost that parity, it doesn't apply here, is the reason why it's more allowed. Okay? Other questions? All right. All right, so the other type of electronic transition that we're going to look at is the type that's called the charge transfer. So here is a movement of electrons from the metal to the ligand or the ligand to the metal. And so we haven't really discussed this idea of metal ligand bonds where the electron source is coming from the metal, but they are allowed. I introduced to you that the theories that we've been focused on have been a bit simplified. Well, this type of electronic transition speaks to the reality that you can have movement of electrons from both species. All right, so let's focus on charge transfers in terms of the selection rules or the electronic rules. These type of transfers are actually both spin and Laporte allowed, okay? So they're spin and Laporte allowed, and as a consequence of that, their extinction coefficients are actually much higher, and they're greater than 1,000 per molar per centimeter. Okay, so you can easily distinguish something that's charge transfer from something that is a d electron transition. Another really important thing is where does it occur energetically? So I already mentioned that d orbital transitions are typically in the visible. When you're talking about transfers, charge transfers are typically in the UV. So there's even a difference in terms of the energy of where you will see them. That doesn't mean that you're not going to see DD in the UV. That can happen. It doesn't mean that you might see some examples dipping into the visible for charge transfers. But I'm giving you just kind of a difference in energy, the intensities, and where you're going to actually see them. All right, so we're going to give just a preview of this. We're not actually go into this much in depth. So in terms of the terminology, when there's a movement or an excitation of electrons from ligand to metal, okay, that's referred to as ligand to metal charge transfer. And you will commonly see in the literature as LMCT. Okay, that's when you see that, that's referring to these type of transitions, where you basically are looking at those electrons getting excited from the ligand into the metal. Now, if we're going to be more formal about this, so a more formal discussion of metal ligand and electronic transitions has to do with the molecular orbital theory, which we have not discussed in this course. So in a more formal discussion of that is the type of molecular orbitals that we're using. And so in that discussion, then, we're looking at the movement of electrons from an orbital that is primarily ligand character, okay, to orbitals that are primarily metal character. The same idea, movement of electrons from ligands to metal, but in terms of molecular orbital terminology, that is how we refer to it. And these type of transitions will typically occur for systems that are pi donors. Okay, what does that mean? Well, those are ligands that have the capacity to have a pi interaction with a metal and move electrons from from those type of interactions into the metal orbitals. You can also see this in sigma donor ligands. I was not trying to exclude that possibility, but more realistically, you will see it with pi donor ligands. All right, so when I say sigma donors, that means a sigma interaction between a metal and ligand. Pi donor, pi interaction. All right, so I'm not expecting you guys to fully appreciate this, but it's just to give us the flavor of molecular orbital theory, which we've all have seen ever since organic chemistry, okay? This idea that you're forming molecular orbitals that are built from the atomic orbitals of the things that are interacting. So you have this collection of molecular orbitals. I'm showing you the example of octahedral, where you have your metal orbitals interacting with your ligand orbitals. You have your collection of orbitals. And so what I'm just going to emphasize is that you're going to have your ligand metal charge transfers that are coming from the orbitals that are lower in energy. In this particular model, the lower energy orbitals are actually ligand character, and they're getting excited into metal character orbitals. Those are typically in these models, they're the higher energy orbitals. And so here I'm just showing you from a sigma model, and to the right, I'm showing you incorporating a pi model, where the origin of the orbitals from and where they're going in terms of the metal orbitals. Okay, so if this is complex, don't worry about it. The key thing is you're moving electrons from ligands to metals. That's the main thing that I want you to appreciate. All right, let's look at the other example. The other example is the reverse, right? Where we're looking at electrons moving from metal to ligands. And so the reality, as I've already alluded to, is that metals can also contribute electrons to bonds, okay? And so there are certain type of ligands that allow for that to happen. And those are the ligands that are pi acceptors, okay? So pi acceptors have that capacity to pull metal electrons in order to form a bonding interaction. All right, so by the terminology, metal to ligand charge transfer, or the abbreviation MLCT. So if we're using formal terminology, this is a transfer of an electron from an orbital with primarily metal character to an orbital with primarily ligand character, okay? And so the type of ligands that are going to facilitate this are pi acceptor ligands. All right. So I'm just going to show you that scary molecular orbital diagram. This is, again, the sigma system. But on the right, we have a system where we have a pi acceptor, okay? And I give an example here of a ligand that is a pi acceptor, which is a carbonyl ligand. Okay, it's a very simple ligand. You've all have actually seen it early on in your study of chemistry, the molecular orbital of that particular simple molecule. It turns out that there is an antibonding orbital of that molecule that has no electrons, that has the capability of accepting electrons from d orbitals. And so that is what's facilitating the movement of electrons from the metal to the ligand. And so we have that. Adding on to what I showed you before, the sources of the metal ligand charge transfers and where are the sources of the metal to ligand charge transfers. So ligand to metal and then metal to ligand here. Okay. All right. Any questions about that?
Transfer of electrons depend completely on ligands, or
it does depend on the type of ligands. So here, let me go all the way back to and you will learn that you will learn that when you come across it in your course, you go all the way back to here. So this spectrochemical series, which I glossed over, actually is a representation of that. So you're going from the left. These are ligands that are pi donors, okay? So if you think about the iodo ligand has these electrons, right? Okay, so you look at your periodic table, those electrons, what orbitals are they from? It's open to everyone. What orbitals are those electrons from? Not D. Have you? S and P, right? S and P. So of those two, which one is capable of pi interaction? P. Okay, so the P orbitals from the iodo ligand allow for the pi donation. So you're going from here, and then in the middle of here, you have ligands that are more sigma donors. And then all the way to the right, you have those ligands. Every one of these ligands has pi donation capability. Because in order to have a sigma donation capability, in order to have a pi interaction, you have to have a sigma interaction. So just because I don't write it there, all of them have the pi sigma interaction. But the difference is their ability to engage in pi interactions. And on the right, we have those ligands that are pi acceptors. And so the carbonyl ligands, the cyano ligand, those ligands have orbitals, molecular orbitals, because they're molecules that are antibonding orbitals that can accept electrons. So to your question, yes, the identity of the ligand does matter. And that's why you can have these type of interactions at the level of pi, depending on the nature of the ligand, okay? All right, other questions? Doubts? All right, so what we're gonna do is we're gonna move on to something that I'd like to present as a way of, in this an overview, a little bit of insight about techniques that you're going to see in the literature, especially when it comes to characterizing metals in a biological system. So this is meant as a sort of an introduction. It's not meant to go into any true depth about the techniques that you can use, but just be familiar with those techniques of isolation and characterization. So what are those tools? And if we want to give it a formality, the chemical biological tools that are available to be able to assess metals in living organisms. What do we have available? And I'm just going to show you just some of the simple ones, but there are now today a lot of really sophisticated techniques that are available, some that we have accessible at our actual university. We're going to skip over this because we already discussed that. So this stems from this idea of the importance of the metalome. So now a lot of the way we categorize the science is by the field of omics. So you're probably really familiar with this from your laboratory, this idea of metabolomics. Well, in the case of metalome, it actually fits into all of the omics, because the reality is that metals are everywhere, and they often play a pivotal role in terms of why a certain omics area is really functional. So sometimes we tend to ignore that. Like for instance, when you take a biochemistry course, you tend to ignore the contribution of the metal. I think if anything, you've only heard of metals probably in hemoglobin. But many of those systems that are discussed in biochemistry actually do incorporate metals. So here in this cartoon representation, we just have this perception then of where you can find metals in different parts of even in the compartmentalized in a particular cell. All right, so this was a terminology that was coined in 2001 that really talks to the entirety of metal and metalloid species in a biological environment. And so this field, what it basically tries to do is give us some insight into quantity and localization. So how much and where. But with this information, we can get some insight as to potential utility, where it's located and what might it be doing. That's kind of the what this field is trying to do. So a lot of the efforts that come into what is metallomics can be broken up into the in vitro. So in vitro meaning things that we do tabletop, like if we're working with an enzyme, or even when we're talking about cells, mammalian cells, that's considered an in vitro system because it's outside of its actual living system. So there, you're looking at things that are, I would say, a bit simplified. What are those methods to look at how the metals are affecting a system? And so sometimes you do experiments where you will mutate something. Let's say you mutate nucleic acid or a protein, and you try to see, well, how that affects a system in a cellular environment. Or you might want to focus on things that are aimed at analyzing and characterizing the bioactivity of something that contains a metal, biomolecule in that case, right? So that would be more in the in vitro realm. But the in vivo realm, that's more complex, right? Especially if you're looking at something that is alive. Now you have to think about what are those tools that are not invasive, that don't cause harm in order to get some insight. And oftentimes, you will perceive things more in an ex vivo context. What does that mean? Well, isolation from a living thing. Like for instance, you have something that is already deceased. You take the organs and you start assessing things from the organs. Still came from a living organism, but it's no longer in a live state. All right, so here you have to think about what are those tools that allow you to do either in vivo or ex vivo for similar purposes: identification, analysis, characterization of the bioactivity of metal-containing biomolecules. Right. So the question is, how do we go about doing this? And so you're going to see a series of studies through the course, things that you will focus on, where things are being perceived either in isolation or maybe in a living context, which again, that's a hard thing to do. So what do people end up doing? Now, if you're focusing on this idea of working with a living system, so whether you have a particular animal model or in the case of bacteria, the bacteria are the actual living system, right? Because that's where they're in the environment they grow. All right, so whether you're going to probe and study directly in those organisms, or you're going to isolate in order to focus on a subset of things that you're interested in. So here, what I'm presenting you is a sort of cartoon representation of a workflow. A workflow is the series of overall steps that you're going to do in order to be able to reach a goal that you have in mind. So in this case, we're imagining this experimental scenario where we want to focus on biomolecules, and we have a particular type of biomolecule of interest. That could be proteins, that could be lipids, depending on what you're interested in. So the question is, how do you go about isolating the molecules of interest, but also how do you go about choosing the tools that are going to help you to assess them? So we have to think about extraction. That's the literal physical process of isolation. We have to think about fractionation, and that is the route of purifying or trying to purify, because oftentimes going from living things, you have a very complex system. So sometimes you don't end up with a pure sample, you end up with a purer sample just to be able to analyze. So then the analysis can be a number of different things. It can be as simple as just identifying the presence of something, or it can be something more than that, whether something is active or not. Okay, so this is basically the thinking about a workflow if you want to focus on biomolecules of interest. All right, so let's go about looking at this systematically. So extraction. So here we have to think about what is going to be the system that we're extracting from. And so are we looking at things that are like, serum, blood itself? Are we looking at cells that have been isolated, and then we're going to focus on that as our system? Or are we going to get tissue that we isolate ourselves, or we buy frozen from a company? We have to decide where are we going to take this from? And then based on that type of system, what are we going to focus on? Are we focusing on lipids, nucleic acids, proteins? Because the reality is that extraction is not something you can do one method, it works for everything. You have to know your molecules, are they water soluble? Are they not? And where are they going to remain active in? Okay. So this idea of trying to get an in vivo picture becomes quite complex. So we have to think about what are those factors in extraction that might perturb that in vivo picture. So oftentimes people will use detergents or organic solvents. Okay, detergents are usually really helpful for keeping things soluble, especially proteins that in the absence of its surroundings will precipitate. Detergents are quite useful. And then for those type of molecules that are not really hydrophilic, organic solvents are used, right? So some of these things can be quite helpful, but they can often result in denaturation. And let's say we're focusing on proteins, that denaturation can even be a precipitation event, or if not a precipitation event, an unfolding event that can mess up what you're trying to actually focus on. And you also have to think about the use of chelators. Right? So we've already alluded to this idea: chelators, ligands that have the capacity of binding metals. One of the classical ones that are used, especially in the field of extraction, is EDTA. Oftentimes, people use EDTA when they collect blood, okay, because EDTA has what important property? Oscar, in the collection of blood. Why is EDTA used? It's okay if you don't know, but what do you think? Why do you think EDTA is used?
En la célula,
For blood extraction.
como que lo inhibe, lo separa.
Well, it can help to keep it from coagulating. Okay, so it's a good anticoagulant. There's other things that are used. But imagine putting EDTA in a system that you're trying to isolate with metals. It can be something that could actually counteract what you're trying to do. So something like EDTA, very useful, especially in the context of trying to inhibit metalloenzymes, because there are a number of very important metalloenzymes that are metalloproteases that are useful for cleaving important proteins as just a natural cycle of basically discarding proteins as they reach their end. But the use of EDTA can actually inhibit a system that you are trying to look at if it requires certain metals. So EDTA is useful for inhibition purposes, but it may actually not be helpful for something that would actually contain metals. Another really important thing that people use as a first step are molecular weight cutoff filters. So these are filters that have membranes, porous membranes, that can separate things based on size. So how big those pores are, or how capable you are to isolating things and separating them. So these are quite useful in that context. Okay. All right, so in the extraction step, so we decide where are we going to extract from here. The cartoon is of cells. We have them in a test tube. And what we want to do is we want to get access to the contents in the test tube. So what we're going to do in a context like this is a step called a lysis. A lysis means the physical breakage of the cells. That can be done chemically, okay? Or that can be done using something that will actually physically rupture them. So that could be using some sort of voltage to break them up, or something like here, I'm showing you the example of a blender that's going to break it up physically, okay? Whatever tool that you use, especially if the cells are pretty small, you have to think about what's going to be the process of doing that. At the end of that process, you're going to have, which is your homogenate. So your homogenate is going to have your maybe your molecule of interest, but it's also going to have a lot of debris, the waste, right? And to move forward, you need to get rid of that waste. The question is, where is your sample of interest? Is it going to be in the soluble part, or is it going to be something that has precipitated at this point? So you're going to use centrifugation as a physical process of separating the liquid from the solid. But then the question is, where is your sample? It's going to be in the solution part, the liquid part, or is it going to be in the solid part? And that's something that you have to think about where you're going to isolate from. All right. So at that point, then you have to start thinking about, okay, my next step. Let's say you have collected your homogenate, your lysate. Next is, what are you going to do to fractionate, to be able to purify and get a pure form of the sample of interest? Well, here then, we're going to take advantage of chromatography, the classical tools that are available. And so what we're going to use is some sort of chemical property of the molecules of interest. So there are many different properties that we can take advantage of. And so in the fractionation process, you can actually use more than one step for purification. So you probably come across this terminology, two-dimensional fractionation, multi-dimensional, okay? What does that mean? What does two-dimensional mean? What do you think?
Anyone?
Hmm?
Anyone?
No, it has to do with the use of two techniques. Okay, so dimension is, one dimension is just like you're using one technique, two dimensions is two techniques, and then three-dimensional and so forth. Okay, so that's just like the number of techniques you use for purification. It's just a fancy way of actually saying that. All right, so let's think about what are the types of chromatography that you can exploit. And so here, these are some of the very basic properties. You can exploit the charge of biomolecules, the size, okay? So we're thinking about proteins, small molecules, obviously a really big dimension in terms of size. You can think about your binding affinity as a property that you can take advantage of. If you know a biomolecule of interest and something that it can bind to, you can take advantage of that. So the different tools, I'm just giving you sort of the classical ones that you are probably familiar with. All right, so when we're thinking about chromatography and something in the context of column chromatography, well, we'll break this out into the phases, where one phase is a stationary phase. And so classically, a stationary phase would be something that is a solid matrix that is porous and has appropriate chemical properties for capturing something that we want to be able to isolate. Now that is in contrast to the mobile phase. So stationary means static, it doesn't move. The mobile is something that actually moves. And so in this case, we're typically using some sort of solvent or solution. If we're talking about water, maybe it's buffered, meaning that it's pH controlled. And that's going to percolate. So percolate is going to move through the actual stationary phase. And oftentimes, the mobile phase is not constant, meaning that the ingredients or the components of that phase can change. All right, so if we're going back to this idea of where we're taking this from, we went from a living system, and at this point, we have used some sort of extraction step. We're going to have something that is a complex sample, okay? Similar to when you're synthesizing something, you may have a mixture of starting material, products, maybe some intermediates. You have a complex sample. And so the idea is that that sample you're going to apply to your column, and is going to get trapped into your stationary phase, and you use your mobile phase in order to be able to elute what you're interested in. All right, so you have this representation here of that. So this is a cartoon representation of loading your sample onto the column. Okay, so everything is packed. Ideally, it's something that you're going to have packed evenly. Okay, but then you're going to use your mobile phase to then start to elute your samples, and the elution order is going to depend on what technique you're using. Okay, so that's not something that I can readily tell you what that order is going to be. It depends on what the technique we're going to use. All right, so let's look at a few examples. One example is ion exchange. Okay, what do you think that means, ion exchange? Jaylene, what does that mean? Has to do with a charge, okay? So depending on the charge, positive or negative, we can take advantage of this. So it can come in two forms. You can have cation exchange, or you can have anion exchange. And so we're taking advantage of the property of molecular charge. So we have to know that something's actually going to be charged in order for to use this. So when we're using the ion exchange technique, then we have to start to think about, well, what's going to be our stationary phase? Because it's going to matter. So for a cation exchange, what we're doing is we're exchanging things that are positively charged. So if that's the case, our stationary phase has to consist of things that are negatively charged, because you're trying to capture positively charged things. So you're using electrostatics as your guide. Whereas in an anion exchange, there you're exchanging things that are negatively charged. So if that's the case, then you need charged species that are positive to be able to capture the negatively charged species of interest. Right? So the stationary phase will dictate whether it's cation or anion exchange. But then what do we do for our mobile phase? How do we remove the charged species that are captured? Well, then what's going to be in your mobile phase has to consist of positively charged or negatively charged things, depending on the technique. But as I was mentioning before, the mobile phase can change over time. And so in the case of ion exchange, your mobile phase is going to change concentration of either cation or anion. And classically, for an ion exchange, you tend to use potassium chloride. So if you're doing a cation exchange, well, we're taking advantage of the potassium to be able to move things that are cationic off of a system. If you're doing anion exchange, you take advantage of the chloride to be able to do the same thing, all right? And so here, this is what's going to be really important. So what's going to happen is that we're going to have a gradient. A gradient means that we're going to start low concentration of the potassium chloride, and we're going to increase it to higher concentration. So over time, that increase in concentration is going to help us in the elution process. So here's just a representation of that, where these colored things are our molecules that are charged, and they're all of different charges. Here, just an example of +2, +3, +4. And here I'm showing you the order of elution, where +2 is coming out first, and then +5 last. As we're applying a gradient, the gradient is represented by, on the right, of potassium, where we're increasing the concentration. And as we increase the concentration, and we're using this, I'm showing this horizontally, as you increase that concentration, things that are more positively charged would elute, all right? But there's also think about in the preparation of this particular technique, cation exchange, what are those things that won't stick to the column? So cation exchange, what's something that won't stick?
That won't stick.
Mhm.
Will the cations stick?
Well, the cations will stick initially because you have everything negatively charged here. Everything's negatively charged, so cations will stick to the column. Because those are what you're exchanging. You're exchanging the cations for potassium, okay? But what's not going to stick?
Will the
Okay, exactly. So anything that's neutral won't stick. Carmen, what else? Anything that's negatively charged. Okay, so those are the things that automatically will be washed out in the very first step without even applying the potassium chloride. Okay, so you have that, the negatively charged, the neutral things, and then the order of elution after that point, once you apply a gradient, will be low positive to high positive. All right, so now let's think about another property, affinity chromatography. So affinity means binding interaction, and we're taking advantage of how strong that binding interaction is. So we're looking at this type of chromatography. So in our stationary phase, we need to have something that is going to be covalently attached with a chemical group, and that chemical group has to have an affinity for the molecule of interest, okay, in order for it to bind. Right? So that's going to be really important. All right, and then our mobile phase will consist of something in solution that's going to help your molecule of interest to lose affinity for what's on the stationary phase. And so I have here a note of what can constitute your mobile phase? It can possibly be an agent with affinity for the chemical group. So maybe something that's going to bind to the actual stationary phase, or it can actually be the free chemical group that's obviously not covalently bound to the stationary phase that will outcompete the affinity to the molecule of interest. So there are different ways that you can take advantage of the affinity in order to allow for elution. And so here, the idea is that molecules will elute as the concentration of the agent or the free chemical group increases, because you're trying to compete with affinity here. So that competition, you will win as you have more and more concentration. So look at an example of this. So here we have an example of something you're trying to purify, which is a glucose binding protein. All right, so something that binds glucose, that is a protein. So if we're thinking about our stationary phase, well, the stationary phase can consist of these beads that have glucose covalently bound to them, okay? So you have your glucose bound to these beads. That's something that is actually, you can find it commercially. So what you're trying to do is isolate proteins that have this affinity for the glucose. And so here in the representation, we have these yellow species as our proteins that have glucose affinity. So on the left, you pack up the stationary phase with the proteins, and then you're trying to elute those proteins. And depending on how many proteins can bind to the glucose, you can have an outside glucose that you add in. Okay, this is glucose obviously not part of the stationary phase. That's going to compete with the stationary phase glucose. And what you're basically going to do is you're trying to outcompete the stationary phase to remove the protein. So here you have the pictures of the free glucose that's bound to the protein and is helping it to remove. So now the glucose is enabling that. So what's going to be the order of elution? What do you think, Carmen? What's going to dictate order of elution?
If you have a glucose bound with proteins, then I would go with size.
Size could have a factor. It won't be the primary one, but it could have a factor because of accessibility, right? But one of the major ones is going to be affinity, because of how strongly something is bound to glucose will dictate how much glucose concentration you need. But size is definitely something that would matter because it's accessibility. Depending on how much space it has to reach it, is going to be another factor. That's why some of these techniques are not 100% going to be perfect. All right. So another classical technique is one based on the hydrophobicity, which means that it repels water, or the hydrophilicity of the actual molecule of interest. Hydrophilicity means was attracted to water. Okay. So this is actually one of the more common ones that are used, at least as a first dimension of purification. So hydrophobicity or hydrophilicity. So when you're using this terminology, this is what you commonly refer to as normal phase liquid chromatography, or this is the more common one, reverse phase liquid chromatography. Okay, so based on that terminology, we're focusing on the stationary phase. The normal phase will consist of polar groups that are on the actual resin, versus the reverse phase will consist of non-polar groups. Okay, so if we keep that in mind, then if you have polar groups as in normal phase, what you're going to be attracted to are things that are going to be polar. Versus on the reverse phase, you're going to have non-polar groups which will be attracted to things that are non-polar. Okay, that's sort of that rule of affinity that we've learned before about like things will prefer to interact with like things. Just like we talked about hard soft acid base theory, the same thing applies here. All right. So when we're referring to the mobile phase, when we're in the context of normal phase, here our solution is going to transition from non-polar to polar, because we're trying to elute things that are more polar, and based on that polarity, we will gauge the elution. But I will note something. You see, I put these in quotes because the reality is that this type of chromatography is based on the relative polarity. Okay, so oftentimes you may be trying to separate things that are really probably non-polar, but the extent of that non-polar is what we're trying to separate. So that's why I put this in quotations, because it isn't always as clear-cut as non-polar separated from polar. It's sometimes a little bit more subtle than that. Okay, but just for the terminology, normal phase, your actual solution will go from non-polar solvent to a polar solvent. versus reverse phase will be the opposite. You're going to go from something that's polar to non-polar. Okay, so that's what the difference is. And so elution for the normal phase will be least polar to most polar. Reverse phase will be most polar to least polar. And that's will be the general difference between those two. And again, of all of these, of these, the reverse phase is the more classical phase that's used. So you hear reverse phase liquid chromatography, you will often see this abbreviation, RPLC. Okay, and that's what that's referring to, reverse phase. All right, so again, that's just an overview of some of the classical techniques. There are others, but I wanted to just give you a flavor of some and introduce a few others that are relevant to metal containing. All right, so how do we go about analyzing? So Javier, you synthesize things?
Yes.
All right, so what is something that you use to analyze some of your products when you synthesize?
Depends on what I'm looking for.
Mhm.
You use spectroscopy,
Okay, what kind?
FTIR,
Mhm.
is
And FTIR, what do you look for?
like the characteristics of my compounds.
Right, so functional groups in your compounds, and that's based on vibrations, all right? Another really classical one is NMR, so nuclear magnetic resonance, but that depends on whether your system is entirely diamagnetic, okay? So here is a classical tool, especially if you're doing organic synthesis, where you take advantage of the nuclei of those organic species. If they're for proton, that's sort of the more classical one that people use. Also carbon-13, but carbon-13 is not as sensitive, so you require more time in order to collect. There's also other active nuclei, and so people actually exploit this for different metals. There's some metals that actually have NMR active nuclei. For instance, vanadium is a classical one that people can take advantage of. All right, so this is a technique that people will often use as a way of characterizing something, and it can be in the solid form, it can be in the solution form. And when it's coming, when it has to do with something that you're isolating, oftentimes you want to do a 2D or two-dimensional approach. So just like, remember what I said to you, you're going to use, probably two different nuclei in order to help you to understand this. All right, but a really important thing about NMR, and one of its major limitations is that, especially in the context of analyzing something that has been isolated, is that you can't use it in its own. You need something to tell you that you identify something in terms of its structural characterization, especially if you have a mixture of species. That can be quite complex. And so another limitation is that you do end up using a lot of material. NMR can be, depending on how you set up your sample, is not destructive. And what I mean by that is that you can recuperate your sample. So in that way, it's actually good. Even though you might need a lot of concentration, you still can regain your sample at the end, especially how you design your experiment. Another tool that's quite useful in the realm of analysis, is used a lot in the omics field, is mass spectrometry. And so typically, this can be seen as a solution state technique because you're looking at things from solution, but the actual technique itself is not a solution. It's once you start measuring the sample. And I'll explain that in a moment. Oftentimes with mass spectrometry, you use fragmentation. And what does that mean? That means that you're going to break your molecules into pieces and you try to, it's like a little puzzle. You take the mass spec of the different pieces to put them together to make sense of the overall big picture of what you have. All right. And so this fragmentation can be done before the experiment. So what do I mean by that? Well, you can use chemical tools to break up something. And that's often done for, like, let's say for proteins. That you often will break up proteins into amino acids, or more realistically into peptides, before you do a mass spec experiment. Or it can actually be done during the actual experiment, especially for small molecules, that you use the power of the energy in the actual instrument to break up and fragment your molecule of interest. So when we're referring to fragmentation experiments, you will see them written as tandem mass spectrometry. You read that word, that means fragmentation. But another terminology used or abbreviation is MSMS. When you see MSMS, that means fragmentation, because the first MS has to do with the mass of the parent molecule. The second MS has to do with the fragments, or the daughter ions. And we'll look at that in a quick moment. All right. And so it typically may require the use of a standard to verify the identification. So this is a technique that you're measuring things based on the mass. But it's a combination of mass by charge. All right, and I'll go back to that in a moment to clarify what does that mean, mass by charge. And if you couple this with liquid chromatography, and actually that's not one of the most useful ways of doing this, coupling with liquid chromatography, you can see the retention times. So coupling that with the standard, you see where is that standard coming from in terms of the retention time, and that can help you to determine the identity. Retention time plus the actual mass spec data will really give you insightful information. And there's actually very little material consumption. So you can see things very sensitive, but it is destructive. All right, so whatever the little amount that you use is going to get destroyed. Another classical tool, although this field X-ray really, and you're going to see another area of X-ray that's really helpful for metal purposes. The technique that can depend on the presence of something in its crystalline form that can actually diffract. And so you're going to get information that's going to be at the atomic level. Okay, so that gives you bonding interactions, bond lengths, and so forth. But oftentimes, crystallography for something for extraction is something that's very difficult. You can try to do it, especially as a method of purification, right? Getting crystals tends to be a process of purification, but it's actually quite difficult. One of the more common ways that people will analyze something that's been isolated is by using an activity assay. All right, so what does that mean? Well, let's imagine that your biomolecule can engage in a bioactive process. Let's say engage it in some sort of enzyme. So you can use an enzyme system to see if after you've isolated your sample, is that sample displaying the activity? That's what it means to assay the activity. And so this is a commonly used approach, especially because it's simple. You don't have to say that by using some spectroscopy, the atomic nature or the molecular nature. Just by seeing that it's active, you know that must be there. Now the question is how pure is a different story. And so oftentimes activity though requires knowing the ingredients required for reconstitution. All right, what do I mean by reconstitution? That means the optimal solution conditions for your actual material to be active. And that is often not so trivial. It may not be so easy to know what you need in solution to gauge activity. So if something is commercially available, like a kit, that can be quite useful in terms of it gives you all the ingredients you may need in order for you to produce your activity assay. But sometimes you have to create it yourself in order to create your at-home method or in-lab method for analysis. All right, and let's get a little bit deeper then. What if we're interested in biomolecules that do in fact have a metal interaction and that metal binding is necessary for function, so that we need to really use conditions that are optimal to retain the metal bound to whatever species that you're focusing on. So we're going to look at a few tools that can help us to get to that point. Let's imagine that we're testing the metal binding affinity of biomolecules post-isolation. So what do I mean by post-isolation? So we're talking about this idea of extraction. So this is after that part. You've already isolated your material, so now we want to characterize it. And we want to characterize this particular property. How strongly does it bind a metal of interest? So one tool, and Oscar can tell you all about this, is immobilized metal affinity chromatography, which is abbreviated as IMAC. All right. So this is a type of chromatography, and as the name implies, is an affinity chromatography. And also, as the name applies, it involves a metal. All right, so here, what you have on your stationary phase is a chelating agent. So this chelating agent is there because it's going to chelate a metal that we're interested in studying. Okay, and then on that chelating agent, we're going to bind a particular metal. All right, so a specific metal that has an affinity for that chelator. And so for us to design this well, we have to be very familiar with hard, soft, acid-base theory for us to know what would be a good chelator metal pair. Then we will take our purified sample, so whatever biomolecule that we're interested in observing its binding to that metal of interest. Okay? And again, it's probably not going to be very pure, probably be a complex mixture, but we try to take advantage of this. And so the elution here, just like with any affinity chromatography, is going to be based on the affinity. And so you're going to use something to elute and break up the affinity between the metal and the biomolecule of interest. The field of IMAC is often applied for proteins, just because they're a simpler system to really work with when it comes to this type of chromatography. All right, let's look at one of the classical ones, especially in the biochemistry field. You probably have seen this back all the way back to your course in biochemistry. So here is a nickel NTA column where your ligand is NTA. So you can see on this resin, so this little blue sphere is our solid resin, so that's our stationary phase, on which there's a covalent attachment of a chelator, okay? So the chelator is this part right here, all right? So let's look at the features of that chelator. What do we have? We have carboxylate oxygen. We have this amine here. We have this other oxygen here. And then we also have this other carboxylate here, right? So it's serving as a chelator because it's binding in more than one spot. We have what looks like it's as many as 4 spots. Okay. So what is the metal here that we have bound? Jaylen, what's that metal? Nickel, see. All right, so we have nickel. All right, so then we think about hard subacid base theory. Nickel is something that's more intermediate. And so this type of ligand is pretty good for nickel, and that's what you typically use, nickel and T8. There's actually other chelators that are used for nickel. All right, but what's actually also important here is that you have 2 coordination sites that are labile. All right, what does labile mean? Labile means that they are free exchange. So that site, you can think of them as free, they're available. So those 2 aqua ligands, they're really not going to be something that will compete much in terms of affinity. So you have 2 coordination sites that you can take advantage of. And that's what people exploit. The nickel to be able to bind biomolecules that have an affinity for something like nickel. And so what you typically will see is the use of these coordination sites to be able to bind proteins that have a histidine tag. And so you probably have heard of this, histidine tags. But you may not really know exactly what that is. So a typical histidine tag will be 6 histidines sequentially, and that will be added to a protein. And it's often done for recombinant protein expression, where you take advantage of the histidines, which we had previously described as being intermediate type of ligands, right? Because you have the nitrogen that has that capability. So you need at least two adjacent histidines to interact with nickel using those 2 coordination sites. And so the use of the 6 histidines has been observed to be optimal in terms of getting that histidine to be able to bind to the nickel. So you'll commonly see a histidine tag with 6 histidines, not just 2. All right. So what are some of the disadvantages of this technique? So this technique is actually quite helpful for protein purification with things that have a histidine tag. But if you're trying to use this technique in a more broad sense, like I want to survey the binding of a metal to different types of biomolecule, this technique is probably not the most efficient, or it won't give you a lot of in vivo reality of what type of interactions might happen. So disadvantages, it only provides you information about the presence of proteins that have metal binding sites, if they even do, okay, if they even have an affinity for a given metal. But it doesn't tell you if that interaction, even if you isolate the metal bound to them, isolate the protein bound to that metal, if that actual interaction even occurs in reality. Okay, because there's a difference between affinity and reality. And then the other thing is that some metal binding sites really are not necessarily accessible. So you might have some compromised binding, especially if you only have 2 coordination sites, because sometimes proteins have to bind as a chelator at more than 2 sites. So you have some amount of compromised binding. So as I already alluded to, this idea that you might have some limitations, especially if the metal binding site is buried, and so it's not accessible to that metal, because that metal is something that needs to be more on the surface, right, in order to interact with the protein. Or if there are additional things that you need for the interactions, a metallochaperone or other cellular components. And the reality is that the cellular environment is quite compartmentalized and is quite stuffed. So you have another layer of things that you can't tell in an experiment like this, where by having this crowding effect, you probably have heard of this crowding effect, that's going to push things to have an affinity. This type of experiment won't allow you to be able to capture. And then finally, if isolated, you might actually have metals already bound to those proteins. So you might need to do a step where you need to strip metals from the molecules of interest before you apply them to the actual column. Because if not, you may get a negative result that is possibly a consequence of a contamination or something that's already bound to the metal itself. Right? So these are going to be some major disadvantages for this type of technique. All right. So as I was already mentioning, this is a pretty inefficient technique as a general approach. It's useful in really specific ways, especially in protein biochemistry, but not necessarily for this type of purpose. All right. So what about other techniques? Well, you can try to directly screen covalently bind metals during or post-isolation. So let's look at an example. Here, we have a type of technique where you're using an elemental analyzer. So what do I mean? You're going to use a technique that's going to detect the element of interest. okay? And so that elemental analyzer will serve as a code detector because you're going to use two techniques. So there's two dimensions of detection here. So let's look at an example. So one example is HPLC, okay, so that's liquid chromatography mixed in with inductively coupled plasma mass spectrometry. All right, so that's a type of mass spectrometry which can be specific for an element. So you're going to take advantage of the chromatography part, which is classical for molecules, and for proteins, it can be quite useful. And you're going to take advantage of the MS part for detecting an element. So in this case, a metal. All right, so what would be our workflow? So we have our sample of interest, we apply our fractionation, and at the stage of fractionation, we will use two methods of detection. So let's say we're doing something that has a metal protein, as an example, right? A metal protein, well, then we'll use a UV detector to detect the protein, okay? That'll be the protein detector. And then the ICP-MS, that's the abbreviation for that type of MS, will be useful for detecting the metal. So there's gonna be something that you split the same sample and try to detect both. All right, so here's this really funny cartoon representation of that, where essentially you have your sample in a tube this can be post isolation, so maybe HPLC was done beforehand, and you're getting there's a fraction that's being collected there. So here's your fraction, and then what's happening is that your sample, which is a solution, will be converted into an aerosol, and that aerosol will be subjected into a high energy space, which is where the argon plasma is. That argon plasma is going to have really hot. This is a technique that you have to be quite careful about, where now is going to change your samples into an ionized form. Because again, mass spectrometry see things by mass by charge. So you're going to think in terms of charge, ionized. So those ions will go through this mass discriminator detector, and that's going to give you the output of what's in there. So that's going to basically destroy your sample. As soon as it hits the argon sample, the argon plasma, excuse me, that's going to completely destroy your sample. So it's going to actually burn it up, and it's just going to bring it into its elemental forms. All right. So it's quite useful in terms of sensitivity. You can detect elements down to the PPT, okay? But keeping in mind, it's destructive. And so what you're going to end up seeing by the this particular MS is the element of interest. So the energy that you're going to use will depend on what element you're focusing on. So if you focus on iron, manganese or copper or something like that, you need to be aware of what type of energy there. All right, so let's give you some examples. So here is an example. I took this from, I think it's from a paper. I forgot I put the reference here. But anyways, what we're looking at is the profile. So these are things that are not going to look so pretty because they're going to be a complex mixture. But what I want to show you is that we're using two detectors. So this is a sample that contains cadmium, and it's a protein sample. So in the protein, we're using a UV detector. All right, so let's remind ourselves of biochemistry. UV, what are we detecting? And what wavelength do we use? Oscar, what wavelength for UV do you use? So you use you use 280. Another common one is 220 and 280. 220 is actually the one that people typically use because 220 will be in every single protein because that is the absorbance of the amide backbone of the protein. So this one is the classical one. 280 is also commonly used, but not all proteins have it because the 280 has to do with the aromatic amino acids. And actually, some proteins don't have aromatic amino acids. So if you have a protein like that, that could be something useful, especially if you see an absorbance, it shouldn't be there. All right. So 220 and 280. Sometimes you will see people go 260 because that's kind of the compromise of the two. You get the absorbance from both. So that's another one, but 220 and 280. So what we have here is a trace. You see that gray trace here? I'm going to try to follow it along. This one. That gray trace is your UV. So that's telling us that we have 7 fractions, okay? And each of those fractions has a UV absorbance. They looked at 254, so they chose something that was closer to 260. So that tells you each of those fractions has a protein, okay? But now, does each of those fractions have cadmium? So the black trace right here, and I'm going to put this in dots. That black trace is everything that has cadmium. Okay, so something like that, and so forth, right? So in the top part, in panel A, we see that Fraction 2 has a significant amount of cadmium, and there's some amount in fraction 3, okay? So maybe we can say those two fractions contain cadmium. In the bottom panel, fraction 4 seems to be, the winner there, okay? So using these two detectors, you can be able to determine whether or not you have your metal of interest. It doesn't tell you if it's exactly the protein that you're thinking about. All right. There's another related type of technique. It's called laser ablation, ICP-MS. So this one is also post-isolation, or it can actually be with a sample itself that's the living organism, but a simple living organism. Laser ablation, an organism, not living. Laser ablation, ICP-MS. So here's just a cartoon representation where you have a laser, where you're using a mirror, and that laser is directing energy onto your sample. Your sample will then become, you get the aerosol, then you get into the plasma, and it will become these ions, which would then be detected by your mass spec, okay? So you're taking your sample, and then you're getting it all into the ion form. That's how we're able to detect the technique. So let's look at ways that this can be applied. So here we have a really ugly gel band. So this is a gel like SDS Page. Let's imagine that we're using SDS Page. That's a technique that's used for purifying proteins. And so I say it's ugly because you don't have these really nicely resolved bands, but this can be a typical protein where like you are band that you put just too much sample and you get the smearing of things. But what are we seeing? We're seeing blots, a few different little spaces here. All right, so we're looking at those. And so you take the different parts of the actual gel and you put the laser on top of it. And so the output is counts per second for the element that you're trying to detect. So here, it looks like we're looking at something that has molybdenum and copper, okay? So proteins that contain molybdenum and copper, and so you try to see along, and see this distance, along the distance of the gel band, what protein has those metals. And so we see a few of them, the one being this one, which seems to have the highest counts per second of both of the metals, the copper and the molybdenum. So this is another way that you can use the technique of ICP in order to, and this is ICP coupled with a gel in order to be able to identify something that might be of interest. Again, this is not identification. It's simply telling you that it has the metals of interest. So here's another approach. This is a literature example. And so here we're looking at brain slices, okay? And so we're looking at these brain slices in which this LAICP, so laser ablation technique, was used. And so what are we profiling here? So we have the same brain slice and we're profiling different metals. We have iron up here. We have zinc, sodium, chloride, or chlorine, in this case, fluorine, phosphorus, carbon. Okay, and we're looking at their profile in that brain slice, so the thin brain slice, and we see just the localization of the actual metals and non-metals, in this case, coming from a rat. And so these type of techniques can be useful post-mortem, meaning after death, to try to gauge if there's a disease condition in that particular sample, because you compare it to the normal profile of something that was healthy versus something that was probably diseased. But this is something you would only know after, right? There's obviously not a diagnosis because obviously this is post-mortem. But it's a way that you can use this technique to give you that information. And you can see a few co-localization of certain elements by this technique. All right, so I'm going to start here, but I'm not going to finish. Mass spectrometry. So this is a technique quite helpful in terms of its sensitivity, destructive. So we've looked at a few examples already of how it destroys. So if we're trying to use it for something that is going to be protein containing or small molecules, how do we use this? So you can directly measure the mass spectrum of the intact metal bound biomolecule if, and very importantly, if the metal bond actually survives purification. So you go through the extraction, you go through the purification with the hope that this actually happens. So you use a mass spectrometry technique that relies on soft ionization. What do I mean by that? So the intensity of the laser that you use, you want to be able to be soft enough that you preserve the coordination to the metal. And so not all techniques have that capability. Some of the techniques result in fragmentation because of the ionization that you use. And so a classical technique for preserving a metal bond is an electrospray ionization. So that's one of the ones that is typically used because you want to try to preserve those metal interactions. And so I'm going to give you an example of where it's been applied, for instance, to gauge metal protein interactions. All right, so a few things to keep in mind. So for optimal and high mass accuracy measurements, you need things that are highly pure, okay? And so there are going to be a lot of conditions that you need to meet in order for you to gauge and see something really well, because this is a technique that's based on having charged species. So it's very important that your samples don't have a lot of salts, because otherwise those are going to compete with what you're trying to detect. And if you have something that's homogeneous, it's helpful. When it comes to proteins, proteins can come and be expressed with different levels of glycosylation. What I mean by that is different amounts of sugars. So you may not have the same mass per protein sample. So it's important that if you're going to work with proteins, you might want to do an enzymatic cleavage to remove any sugars that are bound. But now the technique has really been involved quite well that you can detect things that are at really high mass levels. We're going to start from here in our next lecture. We're going to look at some examples of metals bound to proteins where we're looking at really big protein species. All right, everyone. So I'll see you next time.
What
What do you need? If it's already, please. You can come up to my here. You can come up here. I'm just trying to stop the. Ay, Bayol.